Today, as a representative of Group Black Mamba, I am Diane Montalvo to present our paper, Novel Crystalline Silica Oxide Nanoparticles via Annelids Biopressing of Agro-Industrial Waste. And here are content of my presentation. Now let's start. For our abstract, our paper is all about vermicomposting of annelids to have nanoparticle silica oxide that came from rice husk, sugarcane bagasse, and coffee husk. What we use to get the data is X-ray diffraction, transmission electron microscopy, high-resolution transmission electron, and lastly, dynamic light scattering to show how biotransformation works to create specific crystalline. We also make it eco-friendly and not use the standard chemical method. For our introduction, agro-industrial waste have recently found that it has a potential to use for biotransformation and can be used for fuels and for other materials. And here, it contains amorphous silica that can be transformed into a crystalline nanoparticles. Silica has a major role in some higher plants. The silica absorbs 1% of the dry matter of some of the terrestrial plants, while other plants have 10% and higher. Research even stated that for rice in the form of rice husk, it constitutes 20 to 22% of its total production, 5.08 to 7.08 for sugarcane bagasse, and 1 to 3% for coffee husk. And when the plants die, the silica is became part of the soil and some microorganisms played a role to the gradation of the organic matter and to release its mineral nutrients. There's also other source that can raise this mineralization, and it is through the earthworms. Okay, what can an earthworm help? It can help by producing biohumus. Humus had carbon, or oxygen, hydrogen, and some other minor of minerals. In earthworms, Asenia foetida, or also known as annelids, is a producer of a humus in the condition of environmental control, and the other microorganism can live with it in an anosmic effect. Thus, we made this paper in order to use the annelids into making specific crystal arrays for agro-industrial waste. For objective, the first one is to open an interesting field toward the knowledge of new annelid bioprocess with a primitive metabolism as potential alternative natural nanotechnological technology bioprocess. Second is to develop a novel process for synthesis of diverse nanometric materials. And lastly, is to raise natural sources dedicated to production particles mean biosynthesis. Next is our methodology. For our methodology, we experimented and used rice husk, coffee husk, and sugarcane bagasse and added to vermicompost separately. We used Essenia foetida in 20 degrees Celsius, also with the moisture is around 60 to 85%, and have aeration and put in darkness. We did this at least 1 month, and the humus we obtained was put in a room with 30 to 40 degrees Celsius and dried it. After that, we strained it to have a size of 0.5 millimeters. We also use this to get silica oxide. We get it from the agro-industrial waste without doing vermicompost bioprocesses. We use the same for this procedure, just like the last time. We kinda use commercial synthetic silica oxide aerosol 132 that was provided by Degussa AG to be compared to what we made. Next, to eliminate some organic matter, we calcinated it. The three agro-industrial waste was put in three temperature levels with 500 degrees Celsius, 600 degrees Celsius, and 700 degrees Celsius for 19 hours. We used Lindbergh Eurotherm Model 847. Here, we used the sample with nitric and hydrochloric acid with volume ratio of 3:1. Next, we put 4 ml of acid mix every gram of the calcinated sample to wash some minerals like calcium, potassium, and etc. We achieved it in a room of 40 degrees Celsius and stirring it for whole 4 hours. After that, we filtered it and washed it with distilled water. After it became solid, we dried it using a temperature. To characterize it, we use Fourier transform infrared spectrophotometer, uh, transmission electron microscopy, and high-resolution transmission electron microscopy. For knowing the average particle size, we use dynamic light scattering to carry out element analysis. We use energy dispersion spectroscopy. And lastly, we use X-ray diffraction. For our result and discussion, okay. For this figure, this is from the FIPR analysis that we obtained through rice husk, coffee husk, and sugarcane bagasse that was vermicompost bioprocess, calcinated, and an extraction process. These figures show how this identified the silica oxide. While we're at it, we realized that the temperature didn't matter as they don't infer the analysis. The results suggested that within this FITR, that the silica was released and had the suboxide spreaded correctly. We can also see the peaks at 3,500 and 1,640 centimeters in the are weaker than the peaks belonging to the samples synthesized using vermicompost. On the other hand, figure 2, this one shows the TM image of the silica oxide by vermicomposting. We can see in the picture how clustered they were. This part, the G2H, the silica oxide particles were obtained from agro-industrial without biotransformation, and that is why it has elliptical particles with different diameter, and some have bigger size than the particles we can see in the left side. Thus, it means that doing bioprocessing are needed in order to reduce the size of the particles. Next, this is for HRTEM results of the image of silica oxide particles that was obtained through bioprocess. We can see the nanometric size and the crystal structure of silica oxide. A is the rice husk, B is the sugarcane bagasse. For rice husk, we obtained that the indexation of nanoparticles were related to hexagonal quartz with lattice parameters of 0.343 nanometers, 0.243 nanometers, and 0.198 nanometers. For sugarcane bagasse, it has tetragonal arrangement lattice parameters of 0.2 nanometers, 0.199 nanometers, and 0.142 nanometers. With the result of these two, we concluded that the vermicompost has an important role for silica oxide nanoparticles to have crystalline phases. Next, to confirm the result from TEM and HRTM, we use dynamic light scattering to analyze the particle size. So in this table, the mean of the bioprocessing is 81 nanometers and have no sign of polydisperity, while in without bioprocessing, it showed that the mean is 152 and 254 nanometers and has low polydispersity. So we can conclude that the bioprocess contributes to the particle size reduction and can also provide specific arrangement to the particles. The Annelids metabolism also had a part of this. Next table is about showing the bioprocess of silica oxide particle synthesis, and we can see the amount of silica and oxygen in each agro-industrial waste. For rice husk, it has 41.62% silica and 52.90% oxygen, 23.37% silica and 42.37 for oxygen for sugarcane bagasse, and lastly 41.68% silica and 55.39% for oxygen for coffee husk. It also indicated that other elements that has lower percentage than two like sodium, magnesium, aluminum, potassium, and calcium. Next, here it shows the factograms that came from particles of rice husk, sugarcane bagasse, and other coffee husk. The crystalline nanoparticles were obtained by using two different temperatures with 500 degrees Celsius for the AC and E, while 700 degrees Celsius for BD and F. Let's start with A. This part, we put rice hulls at 500 degrees Celsius. Here, we observe that while not using bioprocess, there are amorphous structure while crystalline phases can be found if we bioprocess it. Hence, this is the possibility to identify some diffraction planes from quartz and others such as tridymite. With the result, it supported the idea of using earthworm to biomineralization mechanism as it can contribute to the atomic arrangement and modifying the original structure for crystalline structure. For B, it also used the rice husk, but it is in 700 degrees Celsius. For not using bioprocess, there is the amorphous structure and only one diffraction plane with low quartz can be seen. For C and D is for sugarcane bagasse. Both of them, the crystalline phases are present, which is the quartz. The only difference is not all the diffraction planes are the same as for 500 degrees Celsius. It appears aluminum phosphate while albite in 700 degrees Celsius. And by that, we assume that the calcination temperature and earthworm metabolism has a huge role to generate different crystalline phases, not only silicon and oxygen, but also other elements. Also, the silica shows several polyforms depending on temperature and pressure. Okay, last for this is the E and F. It is for coffee house. The difference were clearly shown in this part, with the 500 degrees Celsius in part of without bioprocessing, the diffraction peaks appear with tridymite, gypsum, and calcium aluminum oxide hydrate, while quartz, tridymite, cyanide, and magnesium nickel hybrid are detected for with bioprocessing. As for 700 degrees Celsius, without bioprocess appears calcium aluminum oxide hydrate, tricalcilate, and quartz, and with bioprocess are quartz, aluminum phosphate, and calminite. Okay, the last result. This table shows the crystallization percent that was obtained both via bioprocess and without it. We observed that for rice husk, it is not enough to transform it into amorphous phase. However, the annelids metabolic effect increased the crystalline phase as it was 28.47% for 500 degrees Celsius and 16.69% for 700 degrees Celsius. For sugarcane bagasse, it is the opposite form the rice husk. No crystalline phase is lower with bioprocess and higher without bioprocess. Also, the diffractograms showed that some crystalline phases do not correspond to silica oxide, such as zinc phosphate and aluminum phosphate. However, when the bioprocess is not used, particles shows a considerable number of solid silica oxide polymers. Hence, we conclude that the most of the oxygen needed to form silica oxide may come from the earthworms during the metabolic process. Lastly, for coffee husk, there is no clear tendency as for 500 degrees Celsius. The crystalline phase is lower via bioprocessing rather than without. We conclude that the bioprocessing contributes to provide certain area in the nanoparticles. We also concluded that the temperature is not the most important factor for the crystallinity in this kind of nanoparticles. Okay, for our conclusion, we conclude that the annulus is very important to achieve the biotransformation of the amorphous silica. Also, we obtained silica oxide using crystalline nanoparticles using annulus biotransformation through agro-industrial waste, and made it eco-friendly and not using the standard chemical methods. So our paper can be used in the future for more knowledge of new annulid bioprocess with primitive metabolism as potential alternative natural nanotechnology bioprocess to synthesize nanoparticles and nanostructure. Thank you.